Good morning, everyone. I'm Eva Ma from Bosch Research. I have been working with the topic of axial flux machine with JMAG as my primary research tool for quite a while. And today I'm very thrilled to share with you some of my experiences and findings. Yes, today's talk is named Challenges and Advances in Simulation of Axial Flux Machine in High-Speed Traction Drives, a JMAG user experience. Firstly, I'm going to introduce you briefly to axial flux machine and give you the motivation to develop it in the high-speed EV traction application. Secondly, I want to share with you the modeling method I use, design intricacies, and how I conduct the simulation. Indeed, modeling, design, and simulation of this specific type of machine come with their unique challenges. Yes, and I would like to share with you how I navigate through them, provide you some insights into the solution I discovered. As next, I want to present you to a specific topic to simulate the copper loss of this specific type of machine in JMAG. And to make everything full circle, I'm going to present you a recapitulation at the end. So the story of axial flux machine can trace its roots back to the Faraday's disk experiment in 1831. He spun a copper disk between the poles of a horseshoe magnet and connected two wires to its rim and axle. Not only did this experiment prove that moving conductors through magnetic field can generate electricity, but it also gave us a sneak peek into the basics of how axial flux machine work. Fast forwarding to 1834, Morris Jacob invented the first usable electric motor with both the stator and the rotor featuring alternating electromagnets connected in series and with a commutator to ensure its continuous rotation. In year 1889, Nikola Tesla filed the first patent for an axial flux machine, which also laid a solid foundation for this technology's development. An axial flux machine is a very general concept. It's just like radial flux machine. It describes the direction of the main flux, which is in the axial. And I want to present you some distinct machine type within this umbrella term. So starting with the first row, you can see the first two pictures. They are both single stator, single rotor axial flux machine. They differ in their winding configuration. While the first one uses a concentrated winding, the second one uses a distributed winding. And the figure 3 to 5 show us the double stator middle rotor topology. The third one is featuring concentrated winding plus surface magnet, while the fourth one is concentrated winding but plus interior magnets. The fifth one is with ring winding and interior magnet. Moving to the second row, all the 5 machines in the second row belong to the family of double rotor middle stator axial flux machine. We see a ring winding stator nestled between these two surface magnet rotors, and its adjacent model shows us ring winding. The third model is very interesting. It has a coreless concentrated setup, often referred to as L cord. And the fifth one looks also quite interesting. You can see the concentrated winding is separated into 2 parts, inserted from the both side of this stator core. So there is this stator yoke in between, which connects all the stator teeth, both mechanically and electromagnetically. Lastly, we have the yokeless and segmented armature type, which often referred to as YASA type. You can see here all the stator teeth are isolated from each other. So the flux traverses directly between these two rotors without flowing through stator yoke because it doesn't even have a stator yoke. Thanks to the high torque density and unique shape, axial flux machine have permeated in numerous fields. Most representative is in the wind generator, thanks to its high torque density. You will often also find axial flux machine in aerospace application. This is because reducing the weight is a very important goal in aerospace. And yeah, axial flux machine also find utility in the building wheel motor. So I couldn't find any license-free picture with the axial flux machine in the wheel. So it is showing you a radial flux machine, but yeah, due to its compactness and the unique pancake shape, axial flux machine are very suitable for in-wheel motor, not only for a high-end electric vehicle, but also for two-wheelers. In addition to that, axial flux machines are also suitable for various other applications: pumps, fans, centrifuges, machine tools, just to name a few. And they have also become integral in robots, industrial equipment, flywheel elevator hose, just to demonstrate a wide variety of applications. Here it is important to point out that axial flux machines are mainly established in the low-speed traction application, while they find to be extremely effective. And my motivation stems from tangible market needs. So today, the shift towards electric vehicle is evident, but with one obstacle, the cost. Yes, so especially for the low to middle class passenger cars, it has to be aligned, at least the entry cost, with the internal combustion engine vehicle counterpart. So axial flux machine have already a solid reputation for its high torque density, meaning that to generate the same amount of torque, it requires less material, which means cost effective. And but still, there is a gap in our understanding of its characteristic in the high-speed region. And my research is about to push and explore the limit, zooming into the high-speed end of the spectrum. So now we come to the model design and simulation part. To the left, you can see an exploded diagram of my model. Yeah, JMAG actually offers you a bunch of application notes and tutorial in their website. Just like radial flux machine, you can shrink the model size down, applying the, various symmetry condition. Here you see a reduced model from me. I applied one time the natural boundary and 6 times the rotational periodic boundary condition. And you will often find in literature that a lot of research are using 2D modeling method for axial flux machine. So if we take a cut plane at the middle radial of this machine, then we will have a curved face. If we straighten this curved face, then we get a 2D model. So indeed, you can model axial flux machine, at least approximately using JMAG. So just using all the settings for a linear motors. Here, I think most of you must know in 2D model, in any FEM, they assume that the flux distribution is as if the active length is infinite. So the flux is stay in this 2D plane. It cannot escape to the third dimension. And the active length of axial flux machine is not in the axial direction, but in the radial direction, as you can see. So input this active length into the field where you usually input the stack length. You can model it. in 2D, but the real representation of the 2D model will look like this. So there is no variation along the third dimension or the radial direction. And of course, no end winding is modeled here. Yes, you have to, what you have to do is to switch all the condition, like the motion condition from rotation to translation, the torque to force, because there will be no more force in a linear machine. And you need to switch the rotation periodic boundary condition to translation periodic boundary. But here, it's very important. JMAG doesn't allow you to specify the number of periodicity for this translation periodic boundary. So you will have the number 1 in this field, which means which you cannot change. That means you kind of need to handle the data on your own. So what I did is I created my own response data by multiplying the force I got from a 2D simulation by the radius and multiplied by 6, which is the number of periodicity in the rotation. And many researchers also use the so-called 2D multi-layer or multi-slice method to model axial flux machine. If we take the cut plane at inner radial, middle radial, and outer radial, then you will see 3 distinct cross-section and their correspondent 2D model. Maybe you have already noticed that the magnet width and the teeth width varies in this radial direction, while the slot width remain constant. If you only model it with one layer, with the middle layer, then this variation cannot be captured. So my approach of, take an example of the 3-layer approach. I have assigned 1/3 of the active length to each of the 3 2D models and combine the results together at the end. And of course, you can increase the number of layers to 4 to 5, whatever you want. But no matter how many layers you use for modeling the axial flux machine in 2D, you can never capture the 3D effect. So I will give you one example. These 3 pictures are screenshots at the same time instance. So the first picture shows us the magnetic flux density B in vector plot. You can see that it's upwards, meaning that this magnet is magnetized upwards. The second picture shows us the current density within the coil. It's the current is flowing in the clockwise direction, meaning that it created an armature field downwards. And removing all other parts, only keep this stator tooth, then we can see the magnetic field distribution at this time instance. You will see that the fields in the middle part is upwards, while the fields near the regions to the inner and outer radial are downwards. This is because the armature field and excitation field are opposing to each other. So the armature field is pressed by the excitation field, and the flux kind of have to escape in the 3rd dimension. And you have already noticed that the active length of axial flux machine is quite short. So the assumption of having infinitely long stack length or active length does not hold true in this case. And now I want to spotlight on some design intricacies I have experienced. Firstly, unlike radial flux machine, the axial flux machine does not scale with the stack length. It depends more or less on the cube of the outer diameter. So even though compared to its radial flux counterpart, the axial flux machine does save a lot of space in this axial direction. However, if the axial system requirements has a very stringent requirements regarding the radial space, then I can only say, so the outer diameter is restricted. It cuts a lot of torque. Secondly, we have a problem with the eddy current loss within the magnets. So compared to a radial flux machine at the same power range, designed under all the same requirements, axial flux machine does have substantially more eddy current losses within the magnets. This is due to firstly the cost-effective design, which means highly saturated machine, and with the high-speed operation range, plus most importantly the inherent configuration of magnets in the axial flux machine. So it is crucial for design axial flux machine to simulate also the eddy current loss. And of course, because of the 3D effect I mentioned earlier, and there are still a lot of unknown in the analytic method for this machine, it is really hard to determine all the loss components accurately. Of course, if you need to develop a machine, you kind of need to calculate the efficiency very, very accurately. So every loss component needs to be determined accurately. I will give you now a breakdown of the computational effort of this machine. Here you see the small model example I used. This is a 1812 machine, meaning with 18 slots, 12 pores, and I have only simulated 60 degree of mechanical degree of this machine. And if the simulation time really depends on what you are simulating. If you don't simulate any eddy current, then it takes 220,000 mesh elements and takes 10 minutes in a 16-core computer for 31 steps. But if you now want to simulate the eddy current within the magnet, firstly, you need to refine the mesh in the magnet. That means the number of elements increase a little bit to 270,000 mesh elements, but you will see that the simulation times is tripled. The biggest problem arises when you want to also simulate the eddy current within the coils. So the element size is in the order of 10 million. And the simulation time takes 12 hours for 73 steps in 64 cores high performing computer system. So parallel computing, it takes this much of time for one operating point. And of course, this is only for the 1812 machine. If you have a different slot port combination, like in my case, I have also studied the 18 slot 16 port machine. So the smallest repeating unit isn't that small anymore. It turns to this size, and of course, you need to anticipate that the model size increases accordingly. Okay, now let me dive into the copper loss simulation. Yeah, due to the high speed features, we expect a very big AC copper losses, and a method to mitigate this AC copper losses is to connect all the coils in parallel paths if possible. That means you will have a lot of number of turns with small cross section for each coil. And a very suitable technology for this type of machine is the edgewise winding. So you have this rectangular flat wire, which is wound on the flat side, not on the wide side. Yes, and a preliminary 2D study has shown that in this type of machine, you can see the proximity effect is prevailing, and the current density distribution is mainly in the tangential direction, not in the axial direction, which corresponds to the radial direction in a radial flux machine. So this is due to the flux within the slot cannot be assumed to be horizontal. Okay, and due to all the factors I mentioned, the 3D effect and the 2D cannot capture the end winding. So I think at least I need some couple of 3D model, at least for the reference purpose, if I want to develop a simplified method to account for this AC copper losses. Here you can see two two 3D models with coarse and fine meshes within the coils. And if maybe you can notice here, it's the same model, but with different mesh. Finer mesh really capture a lot of details in the current distribution. You see a lot of details here. But the problem is, if I simply implement these size element control within the coils with size control of half of the conductor height, so I will have 2 axial layers for each of the conductor, then the number of element size reaches 11 million. If I want to refine it, I want to have 3 layers, then this number reaches to 26 million. But fortunately, you can draw your own regular hexahedral mesh directly in JMAG geometry editor. So what I did is just to draw the quadrilateral meshes firstly at 2D plane. Then I use a trick by dividing the coils into straight part and curved part, where I apply this phase extrusion for the straight part and phase revolve for this curved part. So at the end, this one single coils takes only 0.67 million mesh element. And another trick is you don't have to simulate eddy current within all the straight coils. You can do that within one coil. Of course, I have done a lot of preliminary study. So the other 2 coils, you can model it with FEM coil, enforcing a homogeneous current. Yeah, by doing so, the total number of this model reduces to 4 million. And here you can see the results of the current distribution. Indeed, you can see the current displacement takes place not only in the active part, but also in the end winding part. And the current distribute mainly in the tangential direction for the active part. JMAG also provides the so-called power simulation license, which allows you to run 100 cases simultaneously, and combining with a special parallelization license, I have conducted the characteristic map with 140 operating points. So basically, I run 100 cases concurrently in our high-performing computer system. And each case can be run at 1 computer node in 16 cores. So in total, 1,600 cores are used for this computation. And it takes, really depending on your mesh quality, on your mesh size, and on the period of time you want to simulate, it takes roughly 2 to 4 days to complete such a map in 3D with eddy current, both in magnets and in copper. Okay, now I want to recap everything. So axial flux machine have a very extensively long history, but they have mainly been established in low-speed traction drives. And today's EV market is really competitive, and all the manufacturers are perpetually seeking for cost-effective solution. Of course, meeting all the requirements at the same time, especially the efficiency-related KPIs. And high-speed axial flux machines have not been widely studied. It requires special design. And the eddy current simulation is non-negligible in this type of machine. So using 3D FEM is necessary if you want to accurately determine all the loss component. But thanks to the advancement of modern HPC and parallel computing, and with some kind of tricks, you are indeed able to compute even multi-query task for this 3D big size model with transient eddy current simulation within a reasonable time frame. Okay. Thank you.
Okay, thank you, Yuen. What a nice presentation. I think that shows really the performance you can get with JMAG. So do you have any question for Yuen? Maybe we have time for 1 or 2 questions. So 2, okay. Oh, 3, so many questions. So Iberard, you are the first one.
Hello. Thank you for your nice presentation. I have a question. You said with a cluster and all the cores, it takes 2 to 4 days for the simulation. What was the objective? Was it an efficiency map or?
Mainly I want to I want to compute the AC copper losses one time accurately, very accurately with all the end windings. So
one operation.
No, the whole map with 140 operating point.
Thanks.
Hello, also from my side, thank you for a nice presentation. I have a question regarding the comparison of 2D and 3D, especially as you did both AC calculations in both, let's say, dimensions. Have you done a comparison between at least the ratio between both AC loss assumptions or results?
Yes.
Are they
I did
comparable?
that. It will be in my next paper.
Okay. Thank you very much.
Okay, so
thank you for your presentation. So I have a question about the eddy current mesh type. So what kind of mesh type using for eddy current? So you are defining the surface edge only, or using this special skin depth mesh for the eddy current? In case of magnet, for example.
I have drawn the meshes in the coils manually, directly in the geometry editor, and all other parts are generated in the designer with the inbuilt with the built-in function like size control, like what is that? Yeah, there are different functionality in the JMAG where you can specify to create automatic mesh. So it's kind of a hybrid. Only the coils I have done it in geometry editor manually using this regular hexahedron meshes.
Okay, thank you.
okay, one last question.
Thanks a lot for the nice presentation. I have a question regarding the lamination types that you used for the Axial Flux Machines. Is it non-oriented material or grain-oriented?
So far, it's NO. It's still NO, but Geo is in the plan.
And did you use isotropic material in the simulations or anisotropic material?
Isotropic.
Oh, isotropic.
Yeah.
But do you think in the radial direction that's it's fair enough to use the same like performance pH curve in the radial direction, the same as in the axial and the circumferential directions?
In the circumferential direction and in the axial direction, you say?
Yep, the circumferential, axial, and radial direction.
Wait a minute. So you don't see the lamination here, but the lamination should be in this direction.
Yeah,
Lamination is in this direction, meaning the flux is actually in the axial direction.
The flux in the axial direction.
Yeah.
That's true. But like then if you use isotropic material, then you allow the flux to escape in the radial direction. And in reality, it's not allowed to go in the radial direction because the material itself is laminated. And then you have the lamination and then some insulation and then another lamination.
Yeah.
And then like the material itself in the radial direction perhaps might have other pH characteristics than the circumferential and axial directions.
Wait a minute. I have not thought about that, but I think we can discuss it later. So this point. Okay.
Okay, so thank you, Yuan. Thank you for your question and interest. Yes.
Feel free to reach out if you have further questions at this email address. Okay. Thanks for your time and attention.
Thank you, Yuan.